talking about Egyptian blue coated liquid marbles reinforced with bisacrylamide coating. Well, ever since I gave this title to my presentation, my research has advanced, so it's going to be incorporated in the presentation, but we took it a little further than that. Is this?
It was work on me. Let's get here.
Oh, I have to. Oh, only the laser works. Okay, then I'll just. Okay, no. Let's see. This one doesn't work either.
It worked for me. I don't know why.
Yesterday, Mac said.
Laser worked, but this for changes lights it doesn't work.
All
For
right.
some reason.
Should I just try?
should
Okay, I'll
try.
just.
Okay, I'll disconnect it. Probably some reset. Maybe it will start work. We'll see. Yes.
Yes, oh, it's
now.
working now. Okay,
Thank you.
thank you. Okay, so a little bit about the background of liquid marbles. So liquid marble is a very small volume of liquid encapsulated by hydrophobic particles. They show reduced adhesion to the solid surface, which means that this renders quick displacements of liquid without leaks. And so these liquid marbles have been a platform for sensing applications. They're an emerging platform due to their facile preparation and their fascinating soft solid properties. Well, these are the papers that discuss these sensing applications. However, these liquid marbles are very easy to break under like intense pressures, which severely limits their everyday use. And here I'm just showing, so this is the first liquid marble that was prepared by French authors. And this is a liquid marble that I made in the lab. And so this is just a generic scheme of how you have to envision a liquid marble. So that's the liquid core, which is usually glycerol or water, and it's encapsulated by hydrophobic nanoparticles. Another background about Egyptian blue, which has also increased, which has also received increasing interest in sensing applications. Egyptian blue is calcium copper tetrasilicate. It's a layered material which can be exfoliated into 2D nanoparticles. And the reason why it's been receiving a great interest in sensing applications is its extraordinary near IR emission at 910 nanometers. You can see the excitation emission spectrum here. And in order to utilize this Egyptian blue in our sensing application, we have to create a uniform coating of micro or nanoparticles. Like I mentioned before, you can exfoliate it into 2D nanosheets. And the uniformity of this coating ensures the performance of a sensor. This is why it needs to be a uniform coating. And we've been, so it's really hard to prepare a uniform coating of 2D nanosheets. It's a lot easier with spherical nanoparticles because of, it's a packed coating, but 2D nanosheets are like a puzzle, so you have to put them together. So the goal of our research is to fabricate a mechanically robust Egyptian blue coated liquid marble as a basis for sensor in water treatment. So now liquid marbles are a great tool to engineer uniform coatings, and there are some criteria that needs to be met. For example, this liquid marble should not disintegrate in water. There must be a uniform Egyptian blue coating so that we receive the same photoluminescence signal, and marbles of the same size are required. And our research focuses on making these liquid marbles mechanically more robust, which means which one possible way to do this is to introduce a more durable core. So how do we fabricate a mechanically robust Egyptian blue coated liquid marble? That's our research question. So first, because liquid marbles require hydrophobic particles, I had to surface modify my Egyptian blue. So first I exfoliated it, some Egyptian blue with HPLC grade water, stirred at 80 degrees C for 2 weeks. Then I let it settle overnight and filtered it through a 0.45 micron filter and dried it in an oven. And then the lipophilization of Egyptian blue, which means making it hydrophobic. I took some Egyptian blue, dispersed it in THF under nitrogen atmosphere. Then I added 10 molar equivalent of trichlorovinyl silane, stirred for 45 minutes, and then hydrolyzed the trichloro groups of the trichlorovinyl silane. And then I isolated the material with centrifuging and washed with acetone and ethanol. And then there was a after process in which I had to grind it into microparticles. So the traditional preparation of liquid marbles that have weak mechanical integrity is you take some of the surface modified nanoparticles, in my case Egyptian blue, you put it on a clean glass disc, you drop a droplet of glycerol or water into the particles and roll it around for about 3 minutes. And this creates a coating of micro and nanoparticles formed on the air-liquid interface. So I just try to point out that, so this is my glycerol core here. This is my Egyptian blue, which has been surface modified with the trichlorosilane compound. However, these liquid marbles had very weak mechanical integrity. So as soon as I put them on water, they completely disintegrated, and we were not able to proceed with the traditional route for preparation. So we started discussions about how to make the liquid marbles more robust. So first we thought of making a more robust coating. So the idea is the same. We have the glycerol core and we have the trichlorovinyl silane modified Egyptian blue. And we envisioned that, with a divinyl polymer, for example, bis-acrylamide, we could link the vinyl groups of the trichlorovinyl silane with the bis-acrylamide. They can react and polymerize in these sides. So I took these liquid marbles and rolled them around in bis-acrylamide and then bis-acrylamide powder and put them under a UV light, 365 nanometers for 3 hours. And we received more sturdy marbles that swelled in water. However, these marbles were not retrievable. They still disintegrated as soon as I touched them with a tweezer. So we moved on and thought that maybe we could make a more robust core for our liquid marbles. So we introduced, instead of just pure glycerol, for the core, we introduced glycerol plus citric acid because I found some papers that cross-link glycerol with citric acid. And the idea was that I would cross-link it within the core with the Egyptian blue coating. So I put these liquid marbles into an oven at 130 C for 2 days. These became really, really robust marbles, so you could not destroy them. However, they did not retain their spherical shape. As you can see, it's like dented, and it doesn't even have like a very well-defined shape. So, and we really needed spherical marbles. So what we thought is that making a more robust core is probably the solution. However, we need to think of something else for the core. So we purchased a commercially available polyacrylic top coat, which is water-based, and Gorilla epoxy glue. And we use these are cross-linkable polymers. We use this as the core and coated the Egyptian blue we coated these polymers with the Egyptian blue. At room temperature, they hardened overnight. So they're actually not liquid marbles anymore. I call them super marbles because they became very, very sturdy. They are also waterproof, and the coating doesn't wash off with water. They're really stable in water. I've been soaking them for about a month now, and nothing's happening to them. So we're really happy with these results that we finally managed to make a very durable core. So to test these in our applications, we needed to perform some fluorescence spectroscopy. The excitation wavelength was 532.14 nanometers. This is the experiment setup. So these are my super marbles in a container, and then we shine a green light upon them. And so we concluded that we managed to make a uniform coating of Egyptian blue, because no matter where we shine the green laser, we get a fluorescence signal all the time. However, our fluorescence signal is not uniform. You can see that here it's around 10,000, here it's a little bit over 20,000, and here it's about 60,000. And we need this signal to be more uniform to be able to use it in a sensing application. And we hypothesized that, so based on scanning electron microscopy images, that you can see there are huge chunks of these Egyptian blue particles on the surface of our marbles. So these crystallite features range from about 1 to 250 microns. Here's the scale bar for 500, and here's the scale bar for 100 microns. And we hypothesized that larger crystallite features might give a stronger fluorescence signal. And this is why we're getting, different fluorescence signals. And to overcome this problem, we thought of reducing the particle size. And so I took my Egyptian blue, the hydrophobic Egyptian blue, and I sieved it through a 75 micron sieve. And you can see that our coating on these marbles are a lot more uniform. They're the scale bar, again, 500 microns and 100 microns. You can see that those huge chunks have disappeared from these SEM images. We got crystallite features of about 1 to 50 microns. And yeah, we're gonna see the fluorescence measurements for this marbles are still in progress, so I'll be able to do them as soon as I return. And so some of the future work that we're planning on doing is, like I mentioned before, reducing the particle size. Maybe it's going to give us a more uniform fluorescence signal using a microsieve. And a later project is we're trying to attach gold nanoparticles because gold nanoparticles of a certain size are anti-fouling agents in water treatment for humic substances. And so we could get like a dual performance sensor for, sensing different kind of ions and an anti-fouling agent as well. And as soon as these gold nanoparticles are attached, we also would like to look into how this influences the near IR emission of the Egyptian blue. Maybe it's going to quench the signal, or maybe it's going to shift it from that 910. And so we're going to be performing some excitation emission matrix spectroscopy that, gives a 3D plot of excitation wavelength, emission wavelength versus the fluorescence intensity. So the conclusions that we can draw is that liquid marbles and Egyptian blue are in emerging platforms for sensing applications. And we looked into how to fabricate mechanically robust Egyptian blue coated liquid marbles. With the traditional route, we got some very weak mechanical integrity marbles. And so we looked into how to make more robust marbles with more robust coating, which included the bis-acrylamide coating. However, the marbles were not retrievable. And then we moved on to making a more robust core. The glycerol and citric acid cross-linking, we could not retain a spherical shape with that. And so we moved on to a cross-linkable polymer with which we received very sturdy waterproof marbles, and the coating didn't wash off as well. And we're looking into reducing the particle size of these Egyptian blue particles and see how it affects the fluorescence spectroscopy and the SEM images. So my acknowledgements go to funds by Tennessee Tech University, the Carnegie Classification of the University, and the Center for Energy Systems Research, Dr. Akira Ueda at Fisk University in Nashville for the fluorescence spectroscopy measurements, and Wayne Hawkins for the SEM measurements. Do you have any questions?
Thank you. Questions? My question is for what this sensor will be, what compounds they design?
So yes, first we try to look into detecting some certain ions. So the problem is, or the research gap here is that currently for water treatment, like water runoff or just rainwater or pond water, when you try to analyze it, you have to take a sample, you have to go back to the lab and then analyze it. So there is no sensing, there is no sensor that provides you an in-field.
Very official sensor.
Yes, there is no sensor currently that gives you an in-field, so right away answer to your questions. For ion content, yes, we looked into, because algae bloom is a really big problem nowadays because of fertilizers, and phosphate ions, nitrate ions, so fertilizer components. We're thinking about using these sensors for that.
Okay, thank you. Any questions? Yes.